I'm very excited to be here today and talk about knowledge graph reasoning, so inferring new knowledge from existing knowledge bases, and especially the application of reinforcement learning in this problem. There are lots of intelligent applications we can build in the enterprise. For example, question answering, semantic search, chatbots. And behind all these exciting applications, knowledge graph is a strong powerhouses. So lots of times we can leverage graphs such as contacts we build from email list or your phone contact list, or product graph, graph which contains product information and how different products related to each other, as well common sense knowledge graphs such as those open domain knowledge graph we can find from Wikipedia or other organizations. There are typically two types of operations we need to run on the knowledge graph. Throughout this talk, I will assume a plain graph structure, which means our graph can be represented in sets of triples. So there are currently there are some advanced knowledge graph, for example, involves meta information, and we leave those out of the scope for this talk. So we can search this knowledge graph, which means given a query, we can simply perform fact lookup using some formal query language such as Sparkle. Like here, we ask, where was Barack Obama born? And within the knowledge graph, we can find Honolulu. However, a lot of times we need to perform much more than this because knowledge graphs, they are intrinsically incomplete. So a lot of times the facts we care about might not present in the graph. So for example, as we've shown here, through the relation, Barack Obama was born in Honolulu, and Honolulu has Hawaii is the capital of Honolulu is the capital of Hawaii. We can possibly infer that Barack Obama was also born in Hawaii. Similarly, we can also infer Barack Obama was born in the United States. Therefore, reasoning is a core problem for knowledge graphs, as very often it is impossible for us to curate or even store all facts possible in a knowledge graph. So in this talk, we mainly talk about reasoning approaches. I will cover 3 different types of reasoning approach which are commonly used for knowledge graphs, which includes knowledge graph embeddings, path ranking algorithms, and sequential decision making. And we can see RL actually plays a significant role in help us learning better multi-hop reasoning algorithms. Okay, so let's dive into knowledge graph embeddings. A lot of you might be familiar with this approach. So knowledge graph embeddings was come out earlier. So it is probably one of the first continuous representation learning algorithms, even before deep neural network got on fire. So what is knowledge graph embedding? So basically in this approach, we learn continuous representations for the entities and the relations in the knowledge graph. And given a fact triple, which contains 2 entities and a target relation, knowledge graph embedding method comes up with scoring functions, which takes the representations for the entities and relations and try to predict a score representing whether the fact is likely to be true or not. Over the years, there has been many fantastic scoring functions being proposed, like shown here. So they have different forms of manipulating the embeddings, and they have different space and time inference complexity. And one thing, one particular interesting knowledge graph embedding approach, which I'm going to cover next, is convolution. It's 2D convolutional knowledge graph embedding. So which is basically using convolution networks to learn the scoring function. Here is just a brief overview of what this graph embedding looks like. So given your source entity, E1, and the target relation, so we represent them both as a dense vector of the same dimension. And the method basically proposes convolutional networks which passes through the concatenation of these 2 embeddings and generates a new representation. And this new representation is used in a dot product with a target embedding E2. And this way we get prediction scores for the potential knowledge facts. And we train such knowledge embedding functions by scoring facts observed in the partial knowledge graphs higher than those not observed. And this method is able to generalize to unseen knowledge graph facts because we will be doing negative sampling during the training. So instead of like pushing the scores of all observed facts down, we sample the negatives. So hopefully the false negatives, their score will eventually going up after the training. This is a SOTA model proposed in 2018, and I believe in the literature there are better scoring functions proposed afterwards. So it would be interesting to refer to the literature for more details. Knowledge graph embeddings have higher accuracy. This has been tested on many knowledge graph benchmarks. However, there are some downsides for this method. One is they lack interpretability because after I got a scoring of a particular knowledge fact, it is hard for me to judge whether the prediction is correct or not, whether I can trust this prediction because there's not so much interpretability around it. Second, this method doesn't perform very well for rare or unseen entities because their entity embeddings, we cannot learn them well. Therefore, during test time, it's hard for such methods to generalize. That's why we came to a second category of algorithm for knowledge graph reasoning, which is parse-based algorithms. For the parse-based algorithms, whenever it tries to predict the possible relations between two entities, it looks at the potential paths in the partial knowledge graph that connecting these two entities and use these paths as features for scoring the likelihood of a particular relation. So for example, as like shown in the example knowledge graph here, so the example knowledge graph is basically a knowledge graph storing information around movies, directors, and actors. And here we want to learn, does Tom Hanks and Steven Spielberg has a collaborator relationship? So path-based algorithm, it will try to find possible paths that connecting Tom Hanks and Steven Spielberg, and try to use those paths to predict whether there could be a direct connection related to collaborator between these two entities. So for example, there are some sample paths shown here. So we could trace a path, for example, Tom Hanks has been cast in the movie, The Post, and The Post has Steven Spielberg as a director. Therefore, Tom Hanks and Spielberg has collaborated before. There could also be some paths which is not very informative. So for example, we saw Tom Hanks is casted in The Post, but the Post is produced in the United States. Well, Steven Spielberg is also lived in the United States, but this is not a very informative path to predict the collaborator relationship. So in terms of how we represented the path, so sometimes we could include intermediate nodes on the path, such as The Post. But a lot of oftentimes we don't need to include the intermediate entity, but only the relations in between. This is because sometimes the intermediate entity is not matter for the inference. So for example, in this case, as long as we know Tom has casted in some movie directed by Steven Spielberg, we can infer that they have a collaborator relationship. We don't need to know what exactly movie it is. So that's why a lot of path ranking based algorithms, they don't include the intermediate entities as a representation. So the knowledge graph is big. There is a immediate question, which is how do we find such inference paths? Obviously, one could do exhaustive search. We could try to find all possible paths connecting the two entities. Sometimes we can efficiently achieve this through dynamic programming. However, the number of paths in a lot of knowledge graph connecting two entities is large. And using such a large feature vector is a lot of times leads to poor learning performance. So that's why later works has been trying to look at how could we effectively identify paths that are potentially informative for our inference. So for example, early works before deep learning has taken off, they have tried data-driven methods. For example, try to come up with discrete heuristics that help us to select the better paths. For example, we only keep paths that is supported by some training facts, or we only keep paths that have leads to some targeted entities on the training set, and use them as features. And in terms of when I say using paths as features, so in the literature, there's also different ways to do that. So sometimes, like we can come up with a score associated with each path. So for example, the random walk probability represented by the path. Or sometimes we could come up with embedding-based approach. We are able to identify the intermediate entity embedding as well as the relation embeddings on the path, and we can effectively aggregate those embeddings to use those as a feature representation for the path. And then we use those all, and we aggregate all the possible paths found between two entities, and use those as features to predict the target relation. So most recently, after deep learning has taken off, and some work has proposed an even more effective way to find such inference paths, which is use reinforcement learning. Because we need to search for informative paths, so why not train a reinforcement learning agent to effectively help us to search the informative path between two entities? This is how this is what a very famous work DeepPath has done. So basically, this work learned a policy-based engine to sample the most informative paths between two entities. And how it works is it learns the policy network and start from the source entity. The agent basically uses policy network to pick the most promising path extension at each step until it reaches a target entity. And we reward the agent by a hybrid reward defined by the following three terms. So one is about search correctness. So basically, if like the path reach the correct target entity, we give the agent a positive reward. Otherwise, we give it a negative reward. And also like regarding efficiency. So a lot of times we prefer short inference paths over long inference paths. So we have an efficiency reward reversely proportional to the length of the path. And also there is a diversity reverse term in the sense that we want the path searched by the agent to be diverse. A new path should be less similar to what the path we have already found. And we can formulate everything as in a reinforcement learning framework and train it using policy gradient. And specifically for this work, it proposes more techniques to help the model learn better. So one is because there is a huge number of paths between two entities. Sometimes if we just naively run policy gradient, the agent basically cannot hit any positive targets and the training cannot go on. So for this work, it uses common techniques used in reinforcement learning, which is first using teacher forcing. We first using bidirectional beam search to find promising paths connecting two entities. And we use supervised learning to force the policy network to first being able to hit those paths found by the bidirectional beam search. And later we retrain the policy network with the reinforcement learning framework. And this method could help the agent learn better. So this is reinforcement learning's application in path finding algorithms. And remember, the end goal here is still identifying informative paths connecting two entities and use them to predict new relations. This path-based algorithms, they're great in terms of they're explainable. And also after several years of development, now their performance is also competitive. They work pretty well when we want to when we know the source and target entities we care about, and we just want to query whether these two entities are subject to a certain relations or not. And also because we notice that sometimes the parse features do not need to include entity information. So this algorithm can work for rare or unseen entities, because if we have an unseen entity, we can just find the path it has connections to the existing nodes in knowledge graph. And then like we can base on the path to infer whether the entity has a relation to the source entities or not. However, a caveat for this type of approach is that they are inefficient for the questions where the source entity is specified, the target relation is specified, but the target entities are not specified. So for example, if instead of asking whether Tom Hanks and Steven Spielberg has collaborated before, we just ask who has collaborated with Tom Hanks. In this case, this type of answer becomes very efficient because we need to enumerate basically all paths between Tom Hanks and any other entities in the knowledge graph and use them for the prediction. So this has proposed an efficiency here. So how do we solve this problem? So this brings us to the scenario where we cast knowledge graph reasoning as sequential decision making. So this is a very clever framework proposed in 2018 by the model called Minerva. So basically, we realized for the problem where the source entity is known and the target relation is known, we can directly formulate it as a sequential decision-making problem. What I mean by that is we can start from the source entity and just directly jump into the knowledge graph and search for the potential target entity. So for example, as here, we start from Tom Hanks, and we sequentially extend the search parse in the knowledge graph until we reach a potential target entity. If we reach a correct answer, then we just stop. How do we train an agent to perform this search? So go from the source entity and stop at the correct target entity. This can also be trained using reinforcement learning. And let's zoom into the formal reinforcement learning formulation of this problem. So typically, when we look at the reinforcement learning framework, we will look at the following 5 components. So the environment, what is defined as a state, what are the actions, how are the state transactions defined, and what are the rewards should we provide to the agent during learning. So in this case, our environment is basically the knowledge graph, and we also have we also know what is a source entity we care about and what is the target relations we care about. And so for the state, is basically the current entity we are at in the knowledge graph. And also we also include the source entity and target relation because we can always see them. So we formulate this as a partially observed sequential decision making process because at each state, we do not assume that we see the entire knowledge graph environment. We basically assume we see the current entity and its neighborhood. So we start from the source entity, and the action space is basically all the other entities connected with the current entity. And our goal is to find a potential edge among all these connections for us to extend the next step. And once the agent finds the next step, it transits to a new state and so on. And basically, it performs this type of multi-hop search in the knowledge graph until it has reached a maximum number of steps. And the entities it arrives in the end is used as a predicted answer. So if the predicted answer is the same as a target entity, then great, the search is successful. So we give the agent reward 1, for example. And if it is not, we could give it a negative reward, or like in this work, we just give it a 0 reward. And we can use policy gradient again to learn which actions to choose at a given state. And so for the policy gradient framework, we basically need a policy function, which defines at a particular state, what is the probability distribution among my next action, like it's shown here. So it's typically parameterized. And for the particular deep reinforcement learning frameworks we talk about, we parameterize the policy function using basically a deep neural network. It takes into account the current search history, which entity I'm currently at, as well as the potential actions I can take. So the history is represented as the sequence of representations of the relation embedding and intermediate entity embedding as C in the history. And we also use LSTM to encode this representation history. And for the action space, similarly, going from my current entity ET to the next state, the action is defined by the edge label we need to traverse and the entity that taken us from that edge. So, and we concatenate the edge label and the entity representation as an action representation. And combining the representations from these two sides, the policy network could output a distribution over all possible actions. So pi theta is a distribution function, and the pi theta over all the potential actions, the value will sum to 1. It's a probability distribution. And so this framework can be trained using a standard reinforced algorithm. So what it does is during training, a sample which, so it has an agent roll out from the target entity multi times. And the way to roll out, we sample how it should perform the next step based on the current policy function. So based on the current distribution of the policy function, we sample an edge it should extend. And we can perform such a rollout many times during training. And if the pass rollout hit a target entity, we give it a positive reward. Otherwise, it receives nothing. So through this way, we can update the parameters defining the policy network by maximizing the expected reward. So all these can be carried out using standard reinforced training. However, as shown in the Minerva work, so models trained using vanilla reinforced learning such way, in terms of performance, they significantly underperform KG embedding methods on several benchmark datasets. So this enables us to zoom into this approach. Because we like this approach, it enables effective power search in knowledge graph. So, and also it is able to produce the answer and the inference path at the same time. So it is a very powerful framework. But because of the stretch of learning both the inference path and the target entity at the same time, the framework is not trivial to train. So we want to examine what are the challenges in training this framework. How could we overcome those challenges and make it better? So first of all, one thing we notice is a sparse reward problem. So remember at the beginning, we said in knowledge graphs, because knowledge graphs are incomplete, so there is a lot of false negatives in knowledge graph. So for example, if like my search path hit Steven Spielberg, but because this is a missing fact in the knowledge graph, so I can only get 0 reward. Although this is Steven Spielberg is actually a correct entity, it should have a better reward than just a 0. But if we just use a vanilla reinforcement learning algorithm and give it a discrete reward, we cannot capture such cases. So that's why in our work presented in 2018, so we propose a reward shaping approach. So instead of like giving this discrete reward to the agent, we want to give them soft rewards. So the idea behind it is we want for each potential target entity the agent is able to hit during its training, we want to provide a soft estimation of whether that entity is likely to be a false negative or not. And how do we estimate that? So recall the knowledge embedding method we surveyed in the first part of this talk. So we basically use a knowledge embedding approach. So we represent every entities in the knowledge graph is represented as an embedding, and we also know the target relation. So we can just call an off-the-shelf knowledge graph embedding functions, and using that scoring function as a scoring function here to estimate the soft reward. And in our work, we use the state-of-the-art convolutional knowledge graph embedding networks. And so basically, for all the potential targets hit by the agent during the training, we run the embeddings of the source entity and the current candidate entity and the target relations through the conv scoring function, and we get to the soft reward estimation. So in this case, if our agent hit potential false negatives, instead of getting 0, it is able to get a continuous reward value. So to help it trains better. The other challenge in this training is called the spurious path problem. So recall that there could be a huge number of paths connecting any two entities in the knowledge graph. Some of the paths, like we reviewed earlier in the talk, some of the paths, they are informative, but some paths are not informative at all, like shown here. So here, path 1 and 2, they actually couldn't. So although they connect these two entities, they are not useful for predicting a collaborator relationship. Only pass 3 is. However, if you just naively run reinforce, because the design of the training algorithm, reinforce has a tendency for the agent to stick to a path which it has seen before and has received a positive reward. Because remember, during training, we sample the path using the current parameters of the policy function. So if a particular path has received a positive reward before, it is likely to have higher policy representation in the policy function, so that your agent will likely be sampling that path more and more often. This way, we ended up reinforce the agent with respect to the spurious path, which is not what we want. We want them to be able to reinforce against the informative path. But effectively identifying the informative path during training is actually very hard. So one thing we could do is we could at least help prevent the agent from being stuck to an uninformative path. So so we do this by using a technique we call action dropout. So basically, we randomly mask certain actions in the policy function to make sure that the agent is able to jump into a different state next time when we do a selection. So for example, as shown here, maybe the current policy function tells us, okay, there's 0.6 probability the agent should go to E2. Not the others. All the other entities have pretty small probability. So here, what we do is we apply a binary mask randomly generated at each training step against the current policy function. And you can see here, our random mask happens to mask the high probability action E2. And once we did the masking, we renormalize and recompute the policy distribution again. And this time, instead of going to E2, the agent has a higher probability to select E1. So this way, we can encourage the agent to explore more diverse paths during training. And if you're familiar with techniques such as epsilon epsilon exploration, so the intuition of this approach is basically similar to that. Basically, to encourage the agent to search for a more diverse set of paths during the training to avoid it from getting stuck to some false positives. With these two techniques, we evaluate algorithms on several KG benchmarks, as shown here. So the benchmarks comes from very different domains, and they were widely used in the community. And they also demonstrate a different degree of connection and different skills. So we compare our method, combining reward shaping and action dropout, with two groups of algorithms. One group is a multi-hop knowledge graph reasoning approach. So this covers the path, for example, path ranking algorithms we surveyed before, and also like algorithms from other multi-hop reasoning families, which we didn't talk about here. For example, like neurological programming and others. So as we see the results, so the dark blue bar is our algorithm, which basically combine vanilla policy gradient with reward shaping. And we see our approach consistently improve over the state of the art for multi-hop reasoning compared to previous algorithms on all benchmarks. So it is comparable or surpass the previous state of the art. And we see that this algorithm, because it simply does, like given the topic entity, it simply runs a search instead of like doing candidate answer enumeration, for example. So this algorithm is very scalable. As we shown here, for several previous algorithms, they actually couldn't scale up on large-scale knowledge graphs. However, we also compare the performance with the family. Sorry, we also compare the performance with the family of knowledge graph embedding algorithms. And as we see those yellow bars, we saw first trend is that typically knowledge graph embedding methods outperforms path-based algorithms on these benchmarks. As I mentioned before, so one explanation for that is learning the inference path is a harder problem than just learning the existing facts. However, you can see our algorithm using this reward shaping, using knowledge graph embedding, we can consistently match the SOTA knowledge graph embedding performance on all the benchmarks. So we are the only one multi-hop reasoning approach that can do this at a time. So this is a pleasant result because we are now combining basically the good parts of both worlds. Our method is explainable, but also performance-wise, it is also become competitive. So I want to show some qualitative results. So let's see a particular example and like what a search path the model is able to find. So again, this is the knowledge graph with respect to actors and movies. And here, so we have a query, which is like we ask the profession of a particular people node inside the graph. So these are the search paths our algorithm is able to return. It returns multiple search paths and multiple possible answers because sometimes we actually deal with very often the case that we have a query and there has to be multiple answers in the knowledge graph. And if we look into the past, so I think the past mostly represent relations such as Laura has, for example, Laura is a winner of SAG award, and Don has also won SAG award before. So Laura and Don should have the same profession. Or Laura and Richard, they have jointly won jointly won an award together. So Laura and Richard, they should have the same profession. So these are all very intuitive and informative reasoning paths, which is great. There are some reasoning paths which are not so great. So for example, like we see Laura has nationality United Kingdom, and Ricky also has nationality United Kingdom. So Laura and Ricky should have the same profession. This is not true, but good thing is like after reinforced learning, we are able to run this type of low competence path lower. And some interesting fact is that so this graph actually represents a clique in the knowledge graph. So it is mostly about the cast crew of the famous British show Downton Abbey. Cool. So in summary, so for the sequential multi-hop reasoning with reinforced learning approach, so this type of algorithm is effective to answer the type of query where your source entity and target relation is known, and you want to know all the possible other entities in knowledge graph that demonstrate such relation with respect to the topic entity. It is able to return multiple predicted answers because once we learn the reinforced learning policy, we can use best first search to search for multiple paths and return the scoring for each path, and therefore effectively return multiple possible answers for the query. It can also be used to solve the type of queries where we ask whether ES and ET demonstrate certain relations or not. But I think one could imagine it takes some extra efforts there because like in this case, we need to do like, given all possible target relations we cared about, we search from the source entity and we see whether ET is in our return search set. So, so I think there are some trade-offs between this group of sequential multi-hop reasoning algorithms compared to the path-based algorithms we just talked about. But like one could choose, depends on the application needs, which family of algorithms we want to use. To summarize for today's talk, so we introduce knowledge graph reasoning techniques because knowledge graph reasoning is critical for knowledge graph-based applications. Since knowledge graphs, they are intrinsically incomplete. So we always need to use inference to generate new facts that are currently not stored in the knowledge base. And reinforced learning approaches, especially nowadays deep reinforced learning approach, they are a strong family of algorithms for learning informative reasoning paths. And these type of algorithm is also time and space efficient. And I also introduced one of the models we propose, which combines vanilla policy network with knowledge graph embedding-based reward shaping. So that one is one of the first algorithm we saw, which performs sequential multi-hop reasoning, but also match the performance of knowledge graph embedding approaches on multiple benchmark data sets. And for future work, there are more exciting works proposed after us. So we should definitely look into more core reinforcement learning research to find ways to resolve a challenge that is either generic towards reinforcement learning or they become knowledge graph specific. But I think overall, this is a very exciting research space still. And also, we have open source algorithms. If you want to play with it, you can visit our open source link on GitHub. Thank you very much.